here underneath the bridge. Okay, there we go, buddy.
Here. Thank you.
Job well done.
Gracias, señorita. I sincerely hope that it was as
This makes me remember of Taxi Cab, Crazy Taxi. Taxi Cab. Remember that game? If you guys ever played it, let me know in the comment section below if you've ever played Crazy Taxi. I think it was pretty much in every arcade. It was a very, very popular arcade game. I know that practically every arcade in Israel had that game, and you could find it very, very easily, and it was very readily available. So,
Welcome aboard the greatest taxi service in the world. Where do you rest your times?
oh God, sorry, it's gonna be a bumpy ride, my friend. You better tip well though, because this is a dangerous ride. Whoa, look at that! You can even do a 180 with him as a customer. That is pretty ridiculous. Imagine if someone drove you like that. That reminds me of that movie with Adam Sandler also, Don't Mess with the Zohan, where he takes a job as a limo driver and he delivers the guy to his hotel opening, but the guy just throws up all over the place. I remember that. Okay, so we're gonna drop off this buddy right here. Oh, okay, I get it now. Every time you get hit or every time you do any type of damage or stuff like that, you lose points. So that's the problem. And my goal is to get to, obviously, sorry, 900 points, I guess, to complete the mission, which is not an easy task, to be honest. It seems like we're at already 3 minutes, so probably not going to get gold, obviously. Am I supposed to just fly slow? No. Faster flying means faster delivery. Faster delivery means I just drop them off.
Thank you.
I'll see you later. Okay. Let's go down here. Whoa. Oh my goodness. No, what are you doing? Come on. Not where I want to be going. I want to go down. Down, I said. Down to the bottom of the sea. Down. Okay, this is horrible. This is a horrible, horrible driving experience. There we go. Finally. Ooh, look at this. Going through the sewers. Okay, go. Speed boost away. Alrighty.
Ride I've ever had.
So I'm going to try to... Really? That was the best taxi ride you've ever had? What kind of taxis have you been riding, my friend? Oh, okay. So if I do tricks, I guess I can regain those points. That's the idea here. Now I got it. Oh my goodness, there's such a quicker way of getting all these points done. Oh, now I feel like a buffoon. I must listen to the rules a little bit more, in a more attentive manner. Okay. So let's get this buddy up and away over here. Okay, there we go. Gonna deliver you down to this area right here. Come on. Give me a way to boost up my points. Alright, and time for the drop-off. See ya. Wouldn't want to be ya. Come on. Oh, I didn't grab him? Okay, it's okay. We'll grab someone down here. Here we go. Look at this nosedive. Not a good idea. Oh, yes, got him. Okay, so now we gotta head this way. And almost there. Just a nice little short ride. Relaxing, you know. Get ready to land, my friend. You're about to be delivered. Great job.
It appears all my tired petitos have taken to their homes. I shall disappear into the clouds as they slumber. Another job well done by Super El Taxi Cabra!
Indeed.
Wow, he is good to his fans.
Yeah, it's not every day you get a taxi ride from Mexico's leading telenovela star.
Speaking of which, El Chu's new flick is on TV tonight. Guerra y Pasión en Tienda de Comestibles. Let's go check it out.
Wait, doesn't that mean War and Passion at the grocery store?
That's an interesting telenovela, that's for sure. War and Passion at the grocery store. Okay. Sounds like a plan. Oh, great. So we only earned a bronze trophy because I was a silly buffoon who didn't realize how the rules work. But I will not let down El Taxi Cabra ever again. Alrighty. So, I guess we continue. We'll come back to the mission, don't worry. We will probably do one where we get diamond levels like a boss. Because I'm a diamond in the rough, or whatever the heck that song goes like. Okay, the next mission is Ticket to Ride. Isn't there a board game called Ticket to Ride? I believe there is one. It's because I watch a lot of tabletop with Will Wheaton, which you should check out because it's fantastic. Alrighty, what happens when a freight train challenges the mighty El Chu to a race across the desert? El Chu brings the heat. Where I guess I shall bring the heat, indeed. Here we go. The loading screen of doom appears once again. It would have been nice if they changed up the images. That would be really cool. I don't know. I'm a big proponent of making the loading screens fun.
Does this have to do with Dusty's close call during the Wings Around the Globe race?
That was in the Himalayas. The vast, barren desert would suggest this is a different locale.
Different locale, different train, and a very different plane.
Alrighty. So it looks like our times are, the best time would be 1 minute and 15 seconds, which sounds kind of crazy. So I'll definitely strive towards that, but I can't promise anything at this point, to be honest.
You think you are faster than the infamous El Chupacabra? You are truly one loco locomotive. Well,
Okay, so I guess I just gotta go through these
off the rails because
lines.
This race is on.
Oh god. Okay, I'm hitting the checkpoints, which
I
is...
throw you, of course, with sheer charisma.
Whoa! 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 Okay, this is crazy. Because I'm just holding the boost button without a stop, so... It's making me nervous because it feels like this train is certainly going very, very fast. I never knew that regular, well, freight trains move this quickly. I thought they were usually a little bit slower. I guess just because this train isn't very loaded with cargo, that's why it is able to maneuver quite quickly. Okay, do not want to be losing my speed at this point. That would be really sucky. Come on, go! Go, 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 go! Okay, that is very low. I'm very close to the train. Whoa, what the hell? Did a train just hit me? That is ridiculous. Come on! Yes! Awesome! Awesome sauceum. Like a boss. So I guess these are different kind of stories in the lives of these characters.
But you never stood a chance against the speed and agility of El Chupacabra. Also, you are a train.
Good point. He is a train. There we go. Achievement unlocked. A silver medal. Achievement unlocked. A gold medal. And achievement unlocked. A platinum medal, which is exactly what we were rewarded with. And look at that. We unlocked ourselves the free flight for Iceland. Sounds cool. I guess now we could go into free flight mode into Iceland, which is pretty cool. We leveled up into amateur ranking. Very cool. That reminds me of the Sonic Kart Racer game. I know that there are a lot of things about this game that reminds me of other games, because they really kind of borrow different features, it seems like. But hey, if you borrow things from a fun game, there's nothing wrong with that. And I remember how there you had to level up your licenses, if you've ever seen that. Alrighty, so next up we've got the Twist of Fate. El Chu must race through tornadoes to win the big race. So let's hear what the story behind this very weathery race. Bum bum bum. Exciting music. Or exciting? No. Wrong choice of words. And that's what happens when English is not your first language. And I should stop singing any minute now.
That's a great shot of Prop Wash Junction.
I bet having a local turned racing superstar like Dusty has really put your hometown on the map.
It sure has. We even get visits from international celebrities now, like El Chu. Of course, the last time he visited, the weather changed so fast, everybody got caught off guard.
Alright, so here we go. Twist of Fate. Ooh, this looks like it's our first race, because as you can see, if we get first place, we will get our platinum trophy. And second, gold, third, silver, etc., etc., etc. And so on and so forth. Okay, so forward, sorry. Okay, so here we go. I guess we gotta hit these checkpoints, right?
He passes through the first checkpoint. Nice
Alrighty.
job. He needs to take control.
Oh god.
And
So it looks like
right
Dusty's
back
in this
into
race as well, right?
He climbs up
And
the ladder and takes a
who
new
else?
spot
I can't
closer
quite
to the top.
make that out. I
Nice
think it's the
skill
Bulldog,
display
right?
here. This gives
Right
our
up at the
racer
front
a
there.
boost up the ladder. He is surprised.
Come
at
on.
the dust of a fellow
Whoa,
racer.
no. I popped that balloon. Not good. Okay. Staying in the front.
Climbs up the ladder and takes a new spot, closer to the top.
Okay, there we
Passing
go.
the midway mark, and this racer has half the gates down and half to go.
Whoa, going through. Coming through. Whoa,
But I thought I'd drop back.
Gate missed. That sucks. I'm sorry about that. Yes, there's a speed boost.
Uses the
Oh,
boost and gains massive
there we go.
momentum.
Nice.
He
Finally.
takes the pole position. Nice going.
Nice. There we go. Come on, another boost. I see it. Now I just gotta get to it. Whoa. Okay, that was very fast.
And our racer
Whoa.
makes it through another
Okay,
gate.
this is
Keeps
crazy.
on going.
Come on, make it through. Make it through. Yes. And ooh, okay, they popped that. They popped that. That wasn't fair.
Race is mine.
Come on.
Folks, we
Yeah,
just witnessed an
yikes.
exciting race.
Damn it.
Not even a tornado can keep El Chu's spirits down.
Except for El Tornado, the luchador.
Yeah, he crushed El Chu the last time they met in the ring.
I would have never pegged you two as wrestling fans. You know it's all staged, right?
What?
It's still real to me, damn it. Some people will get that reference. Most won't. So let's see how we did. In the twist of fate. Bulldog finished first, Ishani finished second, and we finished third. El Chupacabra. Fantastic. I wish we would have finished a little bit far ahead, but we did what we did. And we could have done better. I should have been looking for more speed boost and less not running into checkpoints. So here we go, the final and last mission for El Chupacabra. It is titled Air Force Juan. El Chu plays El Capitan Chu in the feature film Air Force Juan. Can the heroic captain foil a villainous plot to destroy an aircraft carrier? So this sounds like something where we will get to use some weapons. So we will become a fighter jet, or a fighter. I'm not really sure if this is not a biplane, is it? I don't think it is. Does this qualify as a biplane? I'm not certain. I'm not a very big aviation expert, so I'm not certain. But let me know in the comment section below. I'd love to hear the information from you. So it looks like if we earn over 3,550 points, we will earn ourselves a platinum
Did you
trophy.
catch El Chu's latest movie?
Was that the one where he saved the orphans from the villainous long-haul truck during a mudslide?
No, this one starts out with El Chu helping a carrier that's surrounded by mines and out of fuel.
Okay.
Fear not, dear carrier in distress. Capitan El Chupac Juan is on his way
El Chupac Juan.
for a rescue.
Okay, why did the mine
The
just
bad guy
appear?
villains. Well, they will not get away with it. For I,
So what must
as
I
the
do?
good guy hero, shall get my trusty Magneto Gargantuan.
Okay. Whoa. Wait a minute.
No, no, no!
We must turn. Okay, let's turn. I said turn. No. No. Okay.
I have you now. Prepare
So-
to witness as I, Capitan El Chupac Juan, will deliver your fuel units.
Okay. Fuel units to the rescue. Okay, so I should stay away from the mines, obviously, as you can tell. They blow up, and they cause a big boom boom. Not fun.
I must be careful when bringing the fuel. There are nasty, no-good air mines out here.
Okay. I'm gonna stay away from them. Whoa. Whoa, pull it up. Pull it up. Yes. Got one. Okay, second one.
Lágrimas.
Coming right up. Man, these mines certainly do leave off a very strong explosion. Look at that. I love how you could go right down to the water and it leaves kind of like a cool little...
faith in the future. We had to sell this to other people as a way of doing business. We had to show them that airliners could be built this way. So if we didn't have the confidence to pull it out and committed to that, then nobody else would. And it kind of reminds me of the joke about ham and eggs and being committed. You know, the chicken is a little bit committed to ham and eggs, but the pig has got to be fully committed to ham and eggs. So we decided to be fully committed and pull it out.
If the Dryden experiment worked, it would give the aircraft industry the added confidence to use the technology in production aircraft. The Dryden engineers knew all too well that any failure would be disastrous. By using the Apollo computer, the Dryden researchers had the advantage of a proven system. The Apollo engineers had designed their computer to be extremely reliable. It had to be.
This software is really important. One error and you lose the airplane and the pilot. And just think about how many errors you have in today's software in your PC, on your desk, for example. So you can't have any errors in this software. So software becomes as critical as the spar of the airplane. You have to do it right.
By taking advantage of the Apollo program, the Dryden team was able to tap into the earlier effort and adapt the software for their F-8 program.
It's really funny because when you have prepared like we did and we still do, there's almost no apprehension. There's a lot of excitement and you feel good about it and enthusiastic because you're going to do something that somebody hasn't done before. But when I look back on it, I had between 200 to 250 hours of simulator time flying this exact mission. So I was extremely well prepared.
In 1972, Dryden research pilot Gary Creer left his simulator behind and took off for the first flight of an airplane completely dependent upon an electronic control system.
I think we were about 1,000 feet above the ground. Trying to show that I was very relaxed and in control of everything, I calmly said that I wanted 200,000 parachutes and $1 deposited in a Swiss bank, or I wasn't going to return the airplane to Edwards.
The success of the F-8 flights demonstrated that a fully digital flight system could work. But these early flights were not without their problems.
It wasn't very smooth, so the airplane flew very jerky. It was just like driving a car over a bumpy road. You got that feeling in flight every time you moved the flight controls, whereas any other airplane was very smooth. But we weren't out to prove how smooth it could be. We were out to prove how well it worked, and we did that.
It was the Dryden engineers and designers who had the confidence and vision to believe an all-digital airplane could actually work. And it was the test pilots who had the confidence to actually fly such an aircraft. A year later, the Apollo computer was replaced by newly developed IBM computers. But these computer prototypes were not without flaws. There were problems during testing, and on one early flight, one of the computers failed and the plane was temporarily grounded. With the computer problems corrected, the F-8 digital fly-by-wire became a very successful flight research program and proved more than just the feasibility of the concept.
This program certainly changed the way people looked at flight controls and kind of raised the bar. It says this is a standard now. It's been done in Apollo. It's been done on an airplane, an experimental airplane. Why can't we use it in the next fighter and eventually in a transport airplane? And individuals themselves may not even realize that their attitude has been changed. But when you see something actually being done, you start to believe it. And that was certainly the case with this program.
Dryden's experiment gave the technology credibility, and aircraft manufacturers began to take notice. The Dryden researchers encouraged industry engineers and designers interested in discussing the details of how the systems worked. The Dryden experiment did not go unnoticed by the managers of NASA's Space Shuttle program. They chose the same IBM equipment used in the F-8 for the Space Shuttle's flight control system. Even NASA's shuttle engineers became interested in the F-8 fly-by-wire program. And data on the flight control equipment allowed problems in the hardware to be worked out before being installed in the Space Shuttle. The most important contribution made by the fly-by-wire system was in aircraft design. General Dynamics installed an analog fly-by-wire system in a new F-16 fighter. The F-16 is not a very stable aircraft design. The aircraft was built for performance and speed, not stability. The fly-by-wire system kept the plane stable so the pilot could focus on the combat mission.
Stabilize inverted. 0.38, still coming out.
With the electronic control system furnishing stability, designers could reduce the size of some components, such as tail surfaces or wings, and even relocate them. The technology has led to a quantum leap in aircraft performance and design. Today, the most advanced aircraft in the world, from the F-117 stealth fighter to the YF-22, use a digital fly-by-wire system. The B-2A, the world's only stealth bomber has neither vertical nor horizontal tail surfaces. Instead, the aircraft's computer control system tricks the B-2 into performing as if it had a tail section. From the breaking of the sound barrier in the late 1940s to the development of the SR-71 in the early 1960s, the main focus of flight research was to fly faster and higher. In the 30 years since the SR-71 set the world record for high-speed flight, nothing has come close to flying faster. Today's high-speed military aircraft, and even the new YF-22, barely reach Mach 2. The focus in flight research has changed to finding new ways to improve fuel efficiency, flight control systems, and to increase aircraft maneuverability. For a long time, speed was the military aircraft designer's main objective, to be able to attack the enemy and to outclimb him in order to attack again.
Take it, Mike. There's no way you can stay in the loop on that one.
But in a dogfight, maneuverability is as important as speed. The fly-by-wire system and its computers provided a way to build potentially more maneuverable aircraft. The focus is now on finding ways to overcome the limitations on aircraft performance. The tendency of an aircraft to stall and become uncontrollable at slow speeds was the greatest limiting factor in an airplane's maneuverability. The X-29 was designed to investigate a number of advanced aircraft technologies. Built by the Grumman Corporation, the forward-swept wing design, constructed of lightweight composite material, was selected to provide better control, performance, less drag, and extreme maneuverability.
The X-29 continues a very rich tradition of trying novel aeronautic ideas and to measure them, to see if we really understand the processes that we're curious about. So you ended up with obviously a very radical wing sweep, swept forward instead of aft, which people are more accustomed to seeing.
The forward-swept wing weighed more and was not as stable in aircraft compared to other designs. Another problem was that aerodynamic forces could cause the wings to twist, possibly ripping them off from the aircraft.
Grumman put a tremendous sense of craftsmanship into laying that wing up. I mean, that was the first time that I believe, I've been told, that a composite wing, a composite structure was used as load bearing. And you can imagine there were some real concerns. And Grumman approached that very much as an engineering effort, but also very much as a craft. I mean, there were just the quality on that wing, the physical work of laying the laminates up, all hand laid and so forth, was extraordinarily high.
And as we started to fly the airplane, we had people, technical people of some merit, actually tell us, the whole program, that's industry as well as NASA, not to do this, not to fly this vehicle, because it was not possible to design a flight control system with the controllers that were on the airplane, to design it so that it could keep the airplane stable and allow it to maneuver.
If you were to have just mechanical controls on the X-29, that is a cable from the stick to the control surfaces, no human could fly the airplane. It is so unstable, it would immediately diverge up or down, and you would lose control literally within milliseconds. The digital fly-by-wire control, again, restores this stability artificially that was not built in by the aerodynamicist, and allows the pilot to fly the airplane much like he flies any other airplane.
The challenge for the software designers is to write millions and millions of words with tens of thousands of lines of code, all of which have to be perfect, with no errors. Researchers realized if the system failed completely at a certain point, the plane would break up in mid-air before the pilot could eject. Aside from the fact that it is all but impossible to predict every way the system can go wrong no matter how hard researchers try, the pilots don't mind flying these cutting-edge airplanes at all.
It didn't roll fast, it wasn't quick like that, But the fact that if I wanted to roll 2 or 3 more degrees, I could do that, and if I wanted to stop, it would stop within a couple of degrees. That to me was fairly impressive.
It's really hard to pick out single days living as I have for the last 15 years in what is test pilot's utopia here. But I think that first flight in an X-29 was a big event for me. To fly a unique airplane that was, there were only 2 built, that was certainly a highlight.
The X-29 added valuable information in using composites in aircraft design during the 8 years of its research flight program. Today, the use of composite materials provides modern aircraft with more strength with less structural weight.
The X-29 is a good example, although we don't see that airplane in production yet, but it's a very good example of how digital fly-by-wire works, because in getting the maximum performance out of the airplane, it allows new solutions to the problem for the airplane designer, allowing the flight control system to stabilize or to provide the ability for the pilot to control the airplane.
The greatest impact that the engineers, designers, and pilots contributed to the success of the X-29 program was in shattering old ideas about aircraft design by providing the confidence to try unthinkable concepts such as the forward-swept wings of the X-29. The folks at Dryden have again proven that new ideas are possible. The X-29 research project explored one potential design feature focusing on a forward-swept wing to find a more effective aircraft. Cutting-edge programs like the X-29 are always a risky endeavor, but they pave the way for future research into the realm of highly maneuverable fighter aircraft. The ideal situation for a fighter pilot would be an aircraft maneuverable enough to be able to turn inside of an opponent and win. The new technology of thrust vectoring might allow an aircraft that kind of maneuverability. The X-31 research aircraft was built to study an advanced flight control system and demonstrate the value of thrust vectoring technology. A 3-paddle system installed on the aircraft exhaust nozzle allowed the aircraft to make extremely tight turns during test flights, showing the excellent maneuverability of thrust vectoring. Simulator experiments predicted 3 wins for every loss in air-to-air dogfights, demonstrating the tactical advantage that thrust vectoring could provide a combat fighter.
Flying the X-31 in air-to-air, simulated air-to-air combat, having figured out how to use aggression and patience in the right proportions, as you always have to do air-to-air.
In flight combat exercises against F-16 and F-18 fighters above the dry lake beds of Dryden, the X-31 completed rapid 180-degree turns using the advantage of thrust vectoring to deadly effect.
Aircraft is 5 northeast, eastbound 11,000 feet over. Yeah, 111,
Its unique agility during air-to-air combat allowed the X-31 to meet and defeat almost all comers in mock dogfights, maneuvering in and out of turns to win 30 dogfights for each loss. To develop the thrust vectoring technology even further, NASA, Pratt & Whitney, the Air Force, and McDonnell Douglas Aerospace joined together to work on a single program called the Advanced Control Technology for Integrated Vehicle, or ACTIV. This research gave industry designers the ability to study directional control technology with a production engine. Thrust vectoring technology is so effective, it may be incorporated into the next generation of fighters and used to upgrade existing fighter aircraft as well. The modern software used in these experimental aircraft, like the X-31, produce extreme maneuvers never thought possible. But the software is just one more opportunity for something to go wrong.
You really don't know where your problems are going to be. I mean, you try to predict them, but that's why you're doing the program, to find where are the risks, where are, you make compromises in every program, in every experimental aircraft program. And in the case of the X-31, for example, the thrust vectoring airplane that did marvelous things in Paris in 1995 could not have really existed without the digital fly-by-wire control system. It enabled this airplane to do what it did.
Computer technology has increased aircraft performance by tenfold or more, but the systems have become ever more complex, creating new ways for something to suddenly fail. In a shocking reminder of how dangerous flight research can be, this test pilot had only 2 seconds to realize there was a critical problem. An iced-over sensor made the plane's computer malfunction, and the aircraft became uncontrollable. The pilot ejected to safety, but the X-31 was destroyed.
This is still high-risk business. We'd be naive to think that taking these first steps, new configurations, new control systems, new computers, new ways of building airplanes, designing them, integrating with the pilot, isn't serious and risky business. Now, our job is to reduce the risk to where it is small and acceptable. You did everything you thought that was possible, but this is still a human endeavor, and humans are involved, and until we eliminate the human aspect of this, we're going to have mishaps.
Today, the most critical problem that an aircraft could have may not be an engine failure, but a small glitch in the flight control computer. One of the biggest problems with computerized control system aircraft is a phenomenon known as pilot-induced oscillation, or PIO.
Well, a pilot-induced oscillation, or a pilot-involved oscillation, is an oscillation of the airplane plus the pilot, which can be in any one of the axes of control. For instance, it can be a pitch pilot-induced oscillation, which kind of looks like this, or it can be a lateral pilot-induced oscillation, in which the oscillation is in roll. Now, the airplane by itself, left uncontrolled, will not exhibit any of these oscillatory properties. It's only when the pilot plus the airplane as a combination get together in an inappropriate fashion, the oscillation actually occurs.
The differences between human responses and computer control systems have led to some serious situations. The complex fly-by-wire systems that make incredible aircraft maneuvers possible can also, with help from the pilot, send an aircraft out of control. PIO is a dangerous problem in which a number of advanced fighter aircraft and new passenger airliners have been affected. 2 Swedish Gripen fighter prototypes crashed in spectacular fashion due to PIO. A second Gripen was demonstrating the aircraft's maneuverability above a crowd at an air show when the pilot lost control of the jet due to PIO and ejected to safety. In a test flight of the American YF-22 tactical fighter, one of the prototypes ended up skidding down the runway during another PIO crash. Even Boeing's new 777 fly-by-wire transport aircraft experienced PIO problems in its flight test phase. The computerized controls and the pilot can be out of phase. Rapid inputs by the pilot over-control the airplane, leading to a porpoising kind of action which the computer amplifies. Within a split second, the porpoising can escalate out of control and cause the airplane to crash. 20 years ago, before the space shuttle's first launch into space, a critical 5th and final landing test was planned.
The job and the goal was to show that you could land an orbiter on a real concrete runway. All the previous landings had been out on the lake bed. That we could put it down on a spot. So our target area was a white stripe across the runway 5,000 feet from the end.
It was the second flight without the tail cone fairing which covered the engines. The increased drag of the engines resulted in a much steeper approach. As the shuttle approached the runway, pilots Fred Hayes and Gordon Fullerton noticed that their airspeed was about 40 knots too fast.
As we flared out and came up on the on the landing area. He was working very hard to make that landing right on the spot. And that was fortuitous, really, because that high-gain task of really controlling precisely caused Fred to put in quick, sharp inputs to try to keep things right on the money. And it turned out to point out a flaw in the basic control system. One of the reasons you do flight test is to find the flaws. I happened to hear the stick, actually. The sticks on either side of the cockpit are not connected, but I could hear all those roll inputs, and I suggested to Fred, get off the stick and see if the airplane damped.
Spectators, including Prince Charles of England, who were watching the landing near the runway, claimed they witnessed little more than just a poor landing. But the problem was much more serious than just low style points for landings. The shuttle very nearly crashed. Clearly, there was a flaw that needed to be found and corrected before the shuttle could be cleared to launch.
Now, watching the video at the post-flight, I almost fainted. I mean, that's when you're just sitting there watching. To this day, and that probably occurred now 20 years ago. To this day, that video is something that scares me to watch.
All of NASA was put on the problem. The researchers at Dryden already had a fly-by-wire F-8 that used the same flight system as the shuttle. They quickly used the aircraft to investigate the source of the problem in the shuttle system.
And this was the last scheduled flight from the 747, which was the end of the free flight program here at Edwards. And so you really had no other flights to solve this problem. The next flight was going to be a launch to orbit. So pretty much everybody involved in flight controls around the country tried to solve this problem.
Dryden's F-8 test plane experienced a number of harrowing flights. Research pilots put themselves at risk as they repeated the problem by getting their jet to oscillate. During a series of wild flights, the shuttle's problem was identified. The researchers discovered that the time delay between pilot commands and the system's response was too great. A suppression filter was designed at Dryden that solved the potentially dangerous problem. The filter was installed in the research center's F-8, which tested the device and validated it for the shuttle. The device simply suppresses the tendency of the pilot to over-control the system. With the problem corrected, the shuttle program was allowed to proceed on schedule. After more than 15 years of flights, the same suppression filter system still flies on the orbiter. In 1989, a passenger airliner suffered a total loss of its hydraulic system. Unable to control the aircraft's flight surfaces, the flight crew had only one other chance to control the plane. Using the plane's throttles, the pilot fought to control the aircraft. The flight crew used the engine thrust to direct the plane to the nearest airport. As the airliner attempted to land at the Sioux City, Iowa airport, one of its wings struck the ground and flipped the aircraft. Despite a horrifying crash in which those watching believed no one could survive, many of the passengers and crew walked away. Dryden engineer Bill Burcham was on a business trip when he read about how the airliner's pilot, Captain Al Haynes, used the throttles to control the crippled aircraft.
Yeah, the basic concept of flying with throttles is relatively simple. You use, if you want to turn to the right, for instance, you would advance the left throttle slightly and retard the right throttle, and the airplane would roll to the right. And then when you'd rolled as far as you wanted to, you'd have to reverse the throttles to level the wings again.
Pilots can do this now with an aircraft's throttles, but the degree of manual precision is not very good.
You basically just push both throttles forward if you want to climb, and eventually the airplane will climb, but it does it in a kind of a porpoising fashion. If you want to descend, you can pull both throttles back, but again, you descend in a kind of a porpoising flight path that's not really suitable for a safe landing on a runway.
Burcham's idea was a computer program that could provide the kind of precise control needed in such an emergency. A computer program to stabilize the aircraft's flight path and make a very gradual, smooth, and safe descent. Drawing a diagram on a cocktail napkin, in 5 minutes, Bertram outlined how such a system, a propulsion-controlled aircraft system, or PCA, might work. If an aircraft has lost all flight controls, a pilot could get it safely back on the ground by the proper manipulation of the throttles, with the assistance of a computer system to provide stabilization. Bertram attempted to fly Dryden's F-15 simulator using only the throttles. By increasing the thrust, he could make the aircraft climb. Decreasing the thrust, and the aircraft descended. By regulating the thrust between the two engines, he could make it yaw left or right. Bertram approached his friend Dryden test pilot and former Space Shuttle commander Gordon Fullerton to see if he would be interested in helping with his idea.
I was first approached about the idea of controlling an airplane by modulating the thrust, controlling a multi-engine airplane, by Bill Bertram, an engineer here and also a good friend. And he was inspired somehow by the accident that happened when they lost all normal flight controls, but were able to guide the airplane to a crash landing at Sioux City, Iowa. And Bill thought about how could that be done better, maybe to a safe landing, and approached me with the concept. And then it went on from there over a period of years, really, as we thought of ways, theoretically, we tried them in simulators and finally took it to flight in both a fighter and a transport airplane.
Initially, we squeezed all this work kind of in between the cracks, and it probably wasn't until the first year had been completed before we really had approval to spend some serious time on this activity. And at that point, I maybe spent 1 or maybe 2 days a week working on this activity in amongst the normal things I'm supposed to be doing.
There were doubters here that it made sense that it was even possible at all and it was worth any effort to even try. It sounded like a harebrained idea to a lot of people. We saw beyond the initial reaction that it couldn't be done, and got into a simulator where we started to realize some of the problems, but also the possibilities.
Bertram and Fullerton redesigned the system so it was possible for the idea to work. But in using the throttles manually to control pitch, roll, climb, or descend, the changes were not very smooth.
But we found the same problem that the Sioux City crew had, that the precision was just not there to be able to make a safe landing on a first try. It wasn't too long, though, before we decided to try to hook up the computer like we'd sketched out on the napkin. And when we did that, performance improved greatly, and we went from a very, very difficult, kind of unstable flight path to a very steady, solid flight path that was able to make landings on the first try.
After a number of attempts in the simulator, Fullerton was able to land the F-15 on the runway every time. The researchers felt confident in trying the concept in flight. Since the time of the Wright brothers, to really learn about flight requires mounting an engine on a machine and experiencing how a plane reacts in actual flight. Today, because of the tremendous gains in wind tunnel and computer technology, pilots have fewer risky situations to face, thanks to simulators. In a laboratory, researchers can create digital simulations to test flight control systems and train pilots on what to expect during a given experiment. These sim systems create digital models or environments to test the performance of a new aircraft design, software, or maneuver.
Generally, the physical attributes of the simulator are fairly underwhelming. The sophistication of the model and the decisions that we make are pretty far-reaching.
Pilots spend many long hours in flight simulators to reduce the number of surprises they may encounter during actual flight. By the time of the first flight, many potential problems have been identified and solutions developed.
Much of flight research, flight test, is predicting some very bad things and designing your procedures and your instrumentation system and your data systems to find them, see them when they happen, and recover from them. We do so many simulated failures and just terrible failures, failing two computers, failing a hydraulic system, failing the electrical system. The nose gear